all around North America on continental shelves. They have especially a number of examples from the East Coast. And the data set that my lab has been focusing on is a set of bottom trawl surveys conducted for the most part by the National Marine Fisheries Service in the US and Department of Fisheries and Oceans in Canada. It's everywhere from sort of subarctic ecosystems up in the Bering Sea down to the Gulf of Mexico and then up the Atlantic to Newfoundland and Labrador. Each of these red polygons show one of the bottom trawl surveys that we've been looking at. And there are, I should say, similar data sets in Europe as well. I imagine some of the other speakers will talk about them. The earliest one started in the 1960s, and the survey, this is the back deck of one of the survey vessels. They drop a large net off the back, they drag it near the bottom, they pull it up, and they count away the set of species that they find. And it's everything from crustaceans to fish to a wide range of whelks and sea anemones and sea pens and everything else. So just to show you one example from the east coast of the US, this map is for the, can you see my pointer if I move it around?
No.
Or no? No, okay. Okay, so the top, I'll just describe it. The top of the map is in Canada. The bottom of the map is North Carolina, about halfway down the US East Coast. So this is a 1,200 kilometer set of ocean. And the area in red is high biomass of a species called black sea bass in the late 1960s. And then by, these surveys, this particular survey is actually conducted twice a year. But then by 2014, black sea bass had shifted north about 500 kilometers. So it had been off the state of Virginia, and now it's off Rhode Island, Massachusetts. And this is an important recreational fishing species as well as quite an important commercially fished species. And this is during a time that temperatures have been warming quite a bit in the northeast US, as I'll talk about more. So one of the ways that we've summarized these shifts in distribution is by plotting the centroid, so the average latitude, longitude, and depth of the biomass from these surveys for a particular species. I'll talk more tomorrow about the pros and cons of summarizing that way and other kinds of ways that we can summarize range shifts. But what I'll show you today is based off of centroids. So this is the center of the black sea bass distribution marked by this red dot in 1968. And then this arrow shows how far that center shifted between 1968 and 2008. It was shifting at about 50 kilometers per decade to the northeast over those 40 years. But as I mentioned, there are many different species in this survey. So if each of the orange arrows here, the circle at the base shows the center of a species distribution in 1968, and the head shows where that center was in 2008. And we can see that, like black sea bass, some species were shifting rapidly to the northeast, but some were not shifting much at all, and actually some others were even shifting to the south over this period of time. Though the overall average across species in the northeast US over that stretch was 20 kilometers per decade to the northeast, as shown by this red arrow. If we then zoom out to look across many different regions around North America, again, each of the small colored arrows is a taxon within one of the regions, and the heavy black arrow is that average across all the taxa. And most of these data sets, I should say, truncated around 2008, 2010. So there have been a few more years since this figure was put together and this paper came out. But we do see at that time, species in a number of regions were shifting north, but actually in a larger number of regions, species over the period of the surveys have actually been shifting south. So to try to make sense of this variation, and I should say actually this amount of variation across species within a region and between regions is something that many researchers have observed, not only in marine data sets, but also in a large number of terrestrial data sets, birds, mammals, plants, trees. It's a really common feature of data sets when people look at shifts in species distributions. So one of the first things we did was looked at the y-axis here is that mean rate of shift across the species within a region in degrees latitude per year. So that's from that heavy arrow in the map I just showed you. And then that horizontal axis here is the change in bottom temperature over that period of time in degrees Celsius per year. Each dot is one of those regions. And if you, so if you squint, you might say there's a slight tendency for, in regions that were warming, it's more likely that species were shifting north, and in regions that were cooling, it's more likely that species were shifting south. I know we're coming just after a talk in Australia, so north is towards the poles and south is towards the equator. But there's this interesting outlier here, which is the Gulf of Mexico. And on the other hand, in the Gulf of Mexico, there's a really strong geographic constraint. It doesn't make sense actually for species to shift north in the Gulf of Mexico. When it warms, they'd end up in shallow, hotter water or on land. So actually what we've seen is that in general, species are shifting deeper in the Gulf of Mexico. That is also towards cooler water. I'll show you those data in a second. But it does point out how important geographic constraints are on the shifts that we observe, especially at this regional scale. It's also, so if we drop Gulf of Mexico, we can explain about 60% of this variation across regions based on the rate and direction of change in just temperature, average temperature within a region. There's also another interesting case here, the Eastern Bering Sea. Some tendency for shifting north, and yet it's been cooling a bit over the period of this survey. So that starts to make a little bit more sense if we actually zoom in and look at the annual values year by year. So this black line shows how much that assemblage had shifted north or south from the start of the survey in the 1980s up until 2010. The blue line is average temperature within the region. So you can see there's been quite a bit of variability. And if we just look from 1980s to 2005, actually there's some research that had pointed out already that species in the Eastern Bering Sea were shifting north and it had been warming. And we see that trend again when we look at this data set. But actually what happened after 2005 is especially interesting. There was a period of dramatic cooling for about 5 years. We see the assemblage also was shifting south a bit, though not as dramatically perhaps as the temperature is cooling. It seems like there's a bit of a lagged response, at least in this case. But the overall effect is that if we look just at a simple regression through that line, it was shifting north a little bit over that whole period of time and cooling a bit over that whole period of time, which is why we get that case of shifting north and apparently cooling. And yet it starts to make more sense when we zoom in and look at the interannual values. We could also look at changes in depth. So now this is similar to the plot I've already showed you, but the axes are in meters per year. These are bottom trawl surveys, so shifting deeper largely means shifting offshore. And shifting shallower means shifting closer to shore. And what we see is that in places where surface temperature was warming, then the assemblage tends to be shifting deeper, but in places where surface temperature was cooling, the assemblage tends to be shifting shallower. And actually, Gulf of Mexico, in that orange dot, lines up quite well with all the other regions. It's shifting deeper at about the rate we would expect, given how fast it's been warming in that region. On the other hand, sort of looking at these average region-wide changes in temperature and average responses across species doesn't provide us much ability to explain the variation within and within regions as well. So I found that this idea of climate velocity has been quite useful for explaining variation among species. So climate velocity is calculated by thinking about the temperature gradient across space. There's a warm edge shown in red, a cooler edge shown in blue. If you pick a particular temperature, you could draw that line on a map, it'd be an isotherm. And then as that gradient warms or cools, that isotherm moves at a particular direction and at a particular speed. So say kilometers per decade. And that combination of speed and direction is what we call climate velocity. And one of the interesting things that Mike Burrows and other colleagues have pointed out is that if you calculate climate velocity for the last 50 years, and so that's what's being shown on this vertical axis here, and then globally across latitude, so that's the horizontal axis, from the southern hemisphere to the equator to the northern hemisphere there on the right. In the ocean, climate velocities actually are as fast, if not faster, than they are on land. Ocean's in blue and land is in red. And that's partly because there are very weak spatial gradients in temperature in the ocean compared to what we see on land. So species have to move a long distance to make up an equivalent, or isotherms have to move a long distance to have to make up an equivalent rate of warming or cooling. And then, another map from that paper that I think is quite interesting, showing climate velocities all around the globe. Areas in white had climate velocities for the last 50 years that were near zero, and then areas in orange had climate velocities upwards of 200 kilometers per decade. And so you can see there's not only can climate velocities be very rapid in some places, but also there's a lot of variation from one place to the next. Not only because rates of warming and cooling vary quite a bit from place to place, but also because these spatial gradients in temperature also vary. And it's a combination of the two that make up climate velocities. So we can then, using the bottom trawl surveys that I showed you earlier, we can then compare the shift in species distribution, so degrees latitude per year here on this vertical axis, whether they're shifting north, south, or not much at all, against climate velocities calculated just from temperature. So are they shifting, are isotherms shifting north, south, or not shifting much at all? Each of the dots in this figure is a taxa within one of those regions around North America. And this red line actually is not a best fit line, it's a one-to-one line. And you can see that roughly shifts in species distributions have been clustered actually around this one-to-one line. They're clearly not following climate velocity perfectly. They'd fall right on that line if they did. There are many things, many factors that influence shifts in species distributions. And yet we can explain close to 40% of the variation across species based on this one factor, climate velocity, which I think is actually pretty interesting. It suggests that this mosaic of climate velocities helps explain some of this heterogeneity among species. Why are some species shifting north, some south, and some not shifting much at all? We can also, similar to what I showed you before, we can also change these axes so they're in meters per year. So now we're thinking about shifts across depth gradients. Climate velocity is also providing us at least some explanatory ability here, but not quite as much, but to explain why some species are shifting deeper and some shallower. These same figures also let us ask a related question, which is whether populations lag behind climate. And at least in this data set, well, I guess from these figures, if you think about species in this lower right quadrant are not shifting north as fast as we'd expect, and we can measure that lag as the difference from the one-to-one line. Taxa in this upper left quadrant are not shifting south as fast as we'd expect from climate velocity, and yet taxa in these other two quadrants are actually speeding ahead. So we can plot all of those differences from the one-to-one line as a histogram, either speeding ahead or lagging behind. And yet, on average across species in this data set, we actually don't see any evidence for an average lag across marine species. And it is quite different, actually, from what's been reported from especially many terrestrial ecosystems where many groups of species, plants and trees and birds and small mammals often are lagging behind climate velocities. So we've also done a fair bit of work trying to understand whether certain kinds of marine species lag behind. And we focused in particular on what I'll show you today actually is results from the 199 fishes that are in this data set. And what we've done is related the rate of shift in degrees latitude per year. Again, this is calculated from the centroid, which I'm happy to talk about later. May or may not be the best way to do it, but that's what we've done so far. And we can relate it to climate velocity, characteristics of the survey, and then characteristics of the species. So are they demersal and pelagic, commercially fished or not? Is their biomass overall increasing or decreasing? Maximum length of the species, their growth rate, so this is von Bertalanff decay, so individual growth rate, and then overall range size. And what we found using information criterion, and trophic level we looked at as well, is that growth rate was the most important species characteristic. And there was some tendency for slow-growing species to be more likely to lag behind. But I do want to point out that, at least with this data set, it does not provide much explanatory power. If we drop growth rate, the R-squared value goes from 42% down to 41. So really, climate velocity is providing a lot of the explanatory power, at least in this statistical model. So I think we'll have quite a bit of time for discussion and questions, but I did want to talk about one related question that we've been interested in, which is whether, I've been showing you trends over decades, so average trends over decades, but how weather species also respond to just interannual variation in temperature. These are also data from bottom trawl survey, though in particular this one's from the southeast U.S., part of North America that hasn't seen, at least over the survey record, hasn't seen long-term changes in temperature, but there has been quite a bit of temperature variation. Here I'm showing you just results for region-wide biomass, but we have similar results for distribution. And so in this example, I'm showing you standardized biomass on the vertical axis across year on the horizontal axis. You can see that in moonfish, there was an overall increase in biomass through time. But then if we just look at the anomalies from that long-term trend, we can then plot those anomalies on the vertical axis against winter temperature anomaly in this case. And we see that there tend to be more moonfish after a warm winter and fewer after a cold winter. And these particular surveys are conducted in the spring and the summer. And yet, when we tested different seasonal temperatures, winter, spring, summer, it actually turned out that it's winter that has the strongest correlation, not spring or summer. And that holds actually for a wide range of species in this region, because we were interested not just in moonfish, which is just an example, but actually how is the entire assemblage responding to interannual variation in temperature. So to look at that assemblage-wide response, we can plot this positive response of moonfish to a warm winter on this vertical axis. We also saw, we also saw that shrimp had a positive response. Does not show you the icon though. And smooth dogfish had a negative response. And then across all the species, there's a wide variation. Some positive, some negative, some not showing much response to winter temperature at all. And yet, when we then plot that against temperature preference of each species, it starts to make a lot more sense. So we see that species that prefer warm water are showing a rapid positive response to warm winters. Species that prefer cold water are showing a rapid negative response to warm winters. And that shows up statistically in a mixed effects model as an interaction between winter temperature and the temperature preference of each species. So we see this relatively general assemblage-wide response explaining why some species are responding positively, some negatively, some not much at all, and yet the mechanisms behind this seem to vary quite a bit. For one set of species, their juveniles overwinter in estuaries, so very shallow bodies of water exposed to air temperatures over the winter. If it's a cold winter, those estuaries get very cold. And what we see is that there's a much lower survival after a cold winter, and fewer of that cohort then come out onto the continental shelf, where they are picked up by the survey in the following spring and summer. So for species like scarred drum, that seems to be the mechanism. Larger fraction of the cohort survive after a warm winter. In contrast, for other species like smooth dogfish, the mechanism seems to be migration phenology. After a warm winter, they're starting their northward migration sooner, and so there are fewer of them in the southeast U.S. When the survey comes through in the spring and summer. Then I just want to wrap up by briefly mentioning my sense is that you want me to focus on past changes, but I did want to point out one thing in terms of sort of future changes in habitat. We've built species distribution models based on the statistical associations between species, presence, absence, biomass, and various metrics, as well as various bottom habitat metrics, and then projected those forward under a range of global climate scenarios. And one of the interesting things that has come out is if you look at these red arrows, those are the average shift in distribution we expect under a high greenhouse gas emission scenario for each region around North America. And what we see actually is that even though to date we've actually seen most of the large changes have been on the northeast U.S., going forward we expect the largest shifts in distributions from the west coast of North America, where the spatial temperature gradient is relatively weak. So again, back to that point about climate velocities, that even though on average climate models at this point are predicting more or less equivalent warming in each of these regions, we expect large shifts in habitat on the west coast where there's this weak temperature gradient. So you need a large shift in distribution to make up an equivalent amount of warming. I will add in the caveat though that especially the west coast of the US is relatively difficult to resolve in climate models where there's fine scale upwelling that's finer than the coarse scale of most of the global climate models. And then the last thing I wanted to mention is that one thing my lab has been working on quite a bit is making all of these data publicly available. We run a website called Ocean Adapt. The maps I showed you right in the very beginning with sort of red and green areas showing high and low biomass are from Ocean Adapt. And we run this in collaboration with the National Marine Fisheries Service. So every year we pull their data, the data from each of the science centers around the U.S., process their data to standardize it, to make a set of maps and graphs that then show up on the website as animations, animated maps through time. And we're just starting to talk with Fisheries and Oceans in Canada as well to pull in survey data from Canada. And we found that these have been a really useful way, not only for public outreach, we have programs with K through 12 teachers, but also with fisheries managers and with the fishing industry. These maps of them, and they're just all up there. You can explore whatever species or region you're interested in. And then more recently, we've just put up all of the projections of species habitats going forward, again, as animations for, in this case, 686 different species on both coasts of North America to try to help facilitate climate adaptation planning within fisheries management and also within the fishing industry. So with that, I just wanted to thank all the people who've done a lot of this work and made it all possible, and thank all of you for listening, and happy to take any questions. I think we've got plenty of time.
Okay, thanks a lot, Malin. That came in loud and clear. We'll try and make sure that the speakers asking the questions have the microphone, but if you don't hear, just let us know. Okay, question?
Both microphones are muted, so you need to unmute it if you ask a question.
Okay. And if you could introduce yourself for the question.
Okay, hi Malin, this is Paul Spencer.
Hi, Paul.
First of all, I'd like to thank you for getting up so early. According to my clock, it's about 7 a.m. now, so really appreciate it.
No problem.
So I'm thinking about like some of the stocks I work with. There's kind of fine scale stock structure where you have within a species you might have many different stocks, like up and down the west coast of North America of some rockfish. Have you considered how local adaptation would affect some of your results? I mean, you could compare different stocks within a species and see how they respond?
Yeah, no, I think, the interplay between stock structure or sort of meta-population dynamics and the shifts in distribution that we see are a really interesting question. As I was going to talk about this a little bit more tomorrow, but the shifts in distribution that I showed you today, it's a shift in the center of the biomass within a region. So that could be driven by individual adult fish or squid or lobster moving. But it could also be actually just differential population growth between different stocks if there are multiple stocks. So, as you pointed out on the West Coast, it could be that southern stocks are not, actually on the West Coast, the average shift was to the south, at least over this period of these surveys. So, it could be, in that case, it could be northern stocks that aren't growing as fast or even starting to decline a bit, and southern stocks that were growing faster and increasing in abundance. So it doesn't necessarily have to be a movement of individuals. It could just be differential population growth rates across different stocks. So that, I think there's some really good opportunity and important work to be done digging into specific species where we understand the stock structure well and trying to build more of a spatial population dynamics model to capture these, the spatial, the stock structure, but also the population dynamics, rather than just the empirical pattern.
Yeah, I like your examples in the two cases you showed. Like when we think about temperature preference, what does that actually mean in terms of the things that affect a stock? Like you showed an example of one case it's overwinter mortality, another case it's I forget what, phenology, migration phenology.
Yeah.
So.
Yeah, exactly. Exactly. Yeah. No, and I think where we need to move towards are more mechanistic models. It's something that people have been doing a bit of, sort of species by species, but I also think we have ways that we can start fitting. One of the challenges of building mechanistic models for individual species is they need a lot of parameters that often we don't know very well. But I think there are actually some great opportunities to set up a mechanistic model where we understand the processes that are likely important for a given species, given its life history, whether that's overwinter mortality or migration phenology, and then fit those spatial models against the great observational data sets that we have for many of these species. And I think that's an exciting research opportunity.
Okay, Thomas?
Hello, Malin. This is Tom Helser. I'm from Seattle.
Hi.
I haven't met you before, but it was a very interesting talk, and I appreciate your spending time giving it. I have several questions. One has to do with how do you kind of remove the effect of historic fishing and fishing pressure on the stocks, particularly in the Northeast. Since Amendment 5, I think it was in 1995, there was a significant effort reduction policy in place. And then, since that time, there might have been some improvement in the productivity of the individual stock, and therefore an increase in the biomass, which could ultimately cause a shift in what you're seeing.
Yeah, no, I totally agree. Actually, I've got a National Science Foundation grant right now trying to tease those things apart. But I guess in terms of what we've seen, though, and what I showed you today, it's actually part of concern about those linked dynamics is part of the reason that I initially looked at biomass centroids. Not that they're unaffected by changes in biomass, either declines from overfishing or increases from recovery, but range edges, which would sort of be the other natural thing to look at, we did, when I started to look into that, there was some pretty clear evidence that range edges were expanding out when biomass was going up, and range edges were contracting in when biomass was going down. And the centroid was not as strongly related to that, to changes in biomass. And the species traits analysis I showed you right there at the end did account actually for changes in biomass, because I was concerned about effects of fishing, and we also accounted for whether a species was commercially fished or not. So, at least at that broad level, there wasn't strong evidence that fishing was really influencing the rate or direction that species distributions have been shifting. On the other hand, we also know that there are individual cases where it has been important. So in the Northeast US, one of the better studied example is summer flounder, some of the work by Rich Bell. What he's pointing out is that, so summer flounder were pretty heavily overfished in 1990 and have been recovering more or less since then. They've also shifted north strongly, at least the biomass has. And yet, part of that shift, not all of it, but part of it can be attributed to the fact that with recovery, there are now a larger number of large-bodied individuals in the population. You know, the size structure has recovered. And those large-bodied individuals are generally found up north. So that recovery of the size structure is part of what's driven an apparent northward shift. Even within size classes, though, we also see a northward shift. So there seems to be some influence from climate as well. But those linked dynamics between climate and population recovery seem to explain why that species, for example, has shifted north faster than we would have otherwise expected.
Yeah, I think what's compelling is, you know, the fact that you see across a number of species and taxa that, you know, there's an effect with the climate velocity, as you say. The other question I had is your predictive model, and I'm not sure what you're using as a platform to do that. I presume it's a generalized additive model?
What's behind these right here?
Yeah, the future predictive model.
Yep, exactly.
Is it a GAM?
It is a GAM,
Yeah.
yep.
So I think it would be interesting to basically to test your GAM by, I mean, you're only limited with a certain window of time, but you could withhold some data and then see if your GAM can actually predict the distributions from data that weren't used in it to see how well you're doing.
Yeah, and that was part of the testing process. You know, so fitting the models to 80% and then testing against the other 20%.
Perfect.
Exactly.
All right,
Yep.
Thank you.
Yeah, no problem.
Yeah, I have a related question. It's Tara here. So, like a lot of these types of projection models are out there now, so we're starting to see these representations of futures.
Right.
You mentioned you did some testing of the goodness of fit of your projection models, so that's somewhat reassuring. But how widespread is that practice, and should there be some sort of overall standardization or expectation that some model testing has been undergone before these things are just put out there for consideration?
Yeah, and I think, you know, in the community, the standards have gone up quite a bit in the last, you know, even just 5 years. Standards for ways that you test the model and also considering uncertainty. And that's one thing, and actually, I mean, we've been digging into these quite a bit. One of the things we've learned is that we initially were fitting models to both biomass and presence-absence, and yet when the presence-absence part of those models seem to be more robust. To actually we've ended up with more confidence in some ways, the simpler models. The biomass models seem to pick up on, you know, just apparently random correlations with environmental features. You know, they still more or less get the right idea, but not quite as, there's some odd predictions or projections that come out of those. We've also, there's some good papers out there now that sort of lay out best practices, both for species distribution modeling broadly and for marine species specifically. William Chung led a paper recently in the ICES Journal of Marine Science that lays out some of those that I contributed to as well. And one of the other things I should say is that there are many sources of uncertainty in these models, and the paper we published this summer, led by Jim Morley, explored some of those sources, but now we've been going back to think harder about parameter uncertainty in those GAM fit, structural uncertainty in terms of what kinds of species distribution model we use. There's also uncertainty in terms of which climate model you use, as well as which climate scenario in terms of greenhouse gas emissions you use. So I think understanding that range of potential futures is really important, right? We're not we shouldn't be planning for a particular future, but instead a range of thinking about what actions now are going to be useful or robust in the face of that potential range.
Hi, Malin, it's Myron Peck.
Hey, Myron.
I always have a hard time asking you questions. I was going to try to comment about best practices, but you just stole all my thunder with the various different sources of uncertainty that are now being considered, I think, more appropriately. And the mere fact that there's a lot of different types of models that exist now globally than there were 5 years ago, right? So the structural uncertainty is being dealt with better. I guess my question, or I would like to hear your thoughts about how we do move forward. You mentioned it briefly about moving from observations into more mechanistic modeling, and have you considered using traits as a way to do a larger number of species? I mean, I'd love it if we studied every species in the lab and we sort of understood functional niches and realized niches a bit better, but that's unrealistic. But would traits be something, and you mentioned it for a second, I was wondering if you had any thoughts about actually how to do this more mechanistically.
Yeah, exactly. I was going to talk a bit more at the end tomorrow, but actually probably not.
Well, we can wait till tomorrow.
Just perhaps I should. But I was going to say, I do think traits are the way to go. I totally agree with you.
You can set up a teaser.
And I also think that the data set, so one, I agree that traits are important. So, thinking about, which life stages are mobile, things like, just rough traits like body size can tell us a fair bit about growth rates. We can then we can fit some of the parameters we don't know against data. And I think that's what I've been thinking about as well, is that we have these great observational data sets. They can be partitioned to, do some for fitting, some for testing. But the data sets we have are actually, in many cases, better than what researchers have on land, in terms of the spatial extent, the frequency with which they go out. It's really impressive. Plus, for many species, we have size structure. And I think that size structure may actually help us, from a statistical point of view, tease out the mechanisms a bit more. Is it population growth? Is it adult mobility? What are the processes that are driving these? And I think one of the big assumptions of statistical species habitat models or species distribution models, like we're behind those projections I showed you today, is that a species is in equilibrium with its environment. And yet, especially when we have these high frequency observations, there's probably a good chance that they're not, right? That they're catching up through time. And a mechanistic model will help us look at those lags as well and account for them.
Completely agree. I think we have a couple more questions. There was one across. Thank you.
Okay. Hi, Malin. It's Joey Bernhardt.
Hey, Joey.
Hi. I'm going to ask a question, same one that I asked to Greta earlier, and I'm curious about your perspective. I don't know if you heard that, but Greta kind of proposed that we think not only about the traits that make species shifty, but also the properties of the communities in which they're shifting, to think about how receptive or resistant they might be to incoming species. I'm curious if you've thought about this, and if you have a sense, maybe drawing on what we know from invasion ecology, as to what makes the communities receptive to species, and does this help perhaps explain some of the deviations from those one-to-one lines that you presented?
Yeah, exactly. That's something I've been really interested in as well. And actually, Becca Selden, a postdoc in my lab, has been trying to delve into this a bit with these bottom trawl data sets around North America. And at least, I think there's some good examples out there that it does matter, or it can matter in some places. I think of some of Amanda Bates' work with marine protected areas as one example that I think Greta was involved in, but I don't know for sure. In North America, for the continental shelf ecosystems, we've been trying to think in terms of species interactions in terms of like a predator guild, that, you know, if there are lots of predators in the area that a species is shifting into, is that making it more difficult for a prey species to shift in? Or sort of vice versa. There are lots of predators at the trailing edge. Does that trailing edge retreat poleward at a faster rate? And, you know, there's going to be predators in terms of other fish, but also predators in terms of people and fishing. And yet, at least so far, we haven't been seeing a strong signal of either of those effects in this ecosystem. And part of it makes me wonder if it's going to be quite ecosystem dependent. You know, in the communities that we're working in, there's a lot of generalist predators and that are feeding on a wide range of species. So there aren't the strong sort of pairwise species interactions or competition for space that might really amplify those species interactions and sort of invasion resistance phenomena. But I think it's a great question and a really interesting one.
Okay, last question.
Okay, this is Paul again. Sorry to ask you 2 questions, but.
Yeah, Paul.
So I can't remember if you were at the workshop at the ECHO conference in June, the one on bioenergetics, but you know, Kenny Rose. Kenny Rose gave this really, I thought it was a really good talk, and he was basically saying that we need to kind of link the field of movement ecology. I wasn't aware, he just didn't until I heard Kenny's talk. But link that field of movement ecology with fish bioenergetics. I'm thinking about your thoughts about making the models more mechanistic, and I think that's kind of what Kenny was getting to. And some of the data from tagging that Kenny showed is really pretty impressive. And there's people that are really studying, you know, movement at a very fine granular level for individual fish. I mean, is that, like when you say we can make models more mechanistic, is that part of the solution too, or I mean, have you thought about that?
It's a good question. I think understanding how species track environmental conditions would be helpful for understanding how well they can track it in the future. And right, they're going to, if we're talking about adults that are moving, then that individual movement ecology perspective would be really helpful. And I think probably what we need to do though is understand what are the take-home messages from that individual organism perspective that then we can scale up to a population level. You know, because we don't have environmental data at the scale of a fish. You know, we have to make, you know, at least not at large, across large spatial scales. So I think the question is, how do we come up with that? Maybe the mechanistic understanding that then we can scale up to not model every individual fish decision, but the broad population level consequences of those decisions.
Yeah, and that was part of Kenny's, you know, kind of argument too, is that if these IBMs that get more detailed, if they're going to be really useful for studying climate change, we need to kind of link up to global climate change and global populations, populations.
Yeah, and you know, I think that'll be important for species that have a lot of mobility as adults. You know, for other species, you know, if we're talking about urchins, you know, it's going to be long dispersal. So large dispersal modeling, or even just, you know, realizing that they're going to be broadly distributed as offspring, and then you have sort of the next generation that might be growing up in a new place. That process ends up being important for another set of species.
Okay,
Malin. It's like one question from John. Do you want me to answer it quickly, or should I just type them out?
Answer it quickly. Real quickly.
Have I considered breaking it down into small time steps? Might we see greater concordance over more recent times as rates of environmental change increase? It's a great question. I guess I showed you one example from the Southeast US where we do see this interannual variability being important, though we haven't yet looked at sort of other time steps. We've either done long-term trends over decades or interannual, but I agree, thinking about different populations actually based on traits probably will determine the time scale of environmental variation that species are most sensitive to.